All right, so let's go ahead and get started. I'll introduce myself. I'm Daniel Austin. I'm a member of the technical staff at PayPal today. I want to do a little bit of bait and switch here and give you a partial apology on this. The work that we're about to discuss was originally conceived and developed at my previous employer, Yahoo. Over the summer, after I had presented my proposal for the conference, I switched employers. I'd like to actually say thank you to Yahoo and to PayPal both. They have very graciously agreed to let me get up here and talk to you about this work. I want to make sure that everyone understands I do work for PayPal now, but Yahoo has been very gracious in allowing me to go ahead and present this data. They paid for all this work, and they really did an excellent job, and were very gracious allowing me to give this talk. So I want to make that clear up front. And with that, I'm going to switch to the slides that I originally made for this presentation, all of which have purple on them, instead of the typical PayPal logo. So give me a second here just to reload this page. The slide share is a little bit awkward sometimes. So now that I've made my apologies and thanked everyone, I want to actually go ahead and start talking about some cool data stuff. So the first thing is I've scrubbed all the identifiers off of this, no serial numbers or anything. We're just going to talk about Project X. The project actually, of course, had one of these goofy project names that we assigned to things internally. We never want to reveal these goofy project names in public. They're a little too fun. But for the moment, we'll talk about Project X. Our agenda really is that we want to first talk about the problem that we're trying to solve. And I think this is a problem that virtually everyone in this room has had at one point or another. I've heard people in other presentations here at the conference talk about different aspects of this problem, some different solutions than the ones we came up with to some of these problems. I'm hoping that this talk serves as sort of a counterpoint to open some discussion on some of these things. Some of the results that came out of this project were not orthodox. You'll stand up and hear me say things that will be very contentious. I think anybody here from MySQL or Percona was going to look at me bug-eyed when I say some of this stuff because it's not orthodox. And so I'm hoping that that sparks some ideas and interest in your mind, and that this talk actually provides a little bit of counterpoint to some of the other talks. We built a prototype of this. I actually built this prototype over the Christmas of 2010. I had just come back from a long set of speaking engagements. I had nothing to do over Christmas. I set out and wrote this prototype. It was actually nice to sit and write code for a while. I don't often get the opportunity these days to just sort of sit and write code. We'll talk about what we learned. That, of course, is the most interesting part. We'll cover that as part of the talk, but also there will be some summary. Project X. How many people have worked on this project? You know the one that's due yesterday? Everybody kind of worked on that project before? I think so, right? So Project X, of course, the management comes to you and they say, oh boy, we need to collect a lot of data and we got to store it and we want to analyze it and we want to get lots of valuable insights from this data. And it's really a small project, Daniel. Don't worry about it. You don't even need a budget. So no budget for the project, and it's kind of tiny. 10 terabytes working volume. That's actually 1 week's worth of data. 3 terabytes daily inflow. We'll talk about where the rest of the data went as we go through here. That's actually a very tiny data set on Yahoo scale. We have the guys at Yahoo are back there doing 200, 300, 400 terabytes a day, no sweat. This was actually a very tiny project in scale. On the other hand, 3 terabytes, not exactly in the real world, a tiny database. Of course, it's supposed to be cheap. There's no budget. It's supposed to be fast. This is the performance team, and of course, it's got to be good. Pick one of those. You can't have all 3 of them, or, well, how do you explain that to the management? We decided we were going to optimize the whole thing for query speed. This is a business intelligence system. We want the people that were the primary actors, the analysts, the people who wanted the data, to get everything quick. They were the primary actors. We optimized it for them. The next most important feature was that we optimized for ETL speed, given the very large volume of data. And this is all text data, unfortunately. Right? We had to make sure that we could process all that data and get it into its data storage destination in a one-day period. That's not necessarily as easy as it looks. Obviously, the project needed to be done before it started. We've all worked on this project at some point, right? So what did I do? I went and built a prototype over Christmas, did not take any time off. Now you get to hear about the wonderful results. And they actually were pretty wonderful. I was surprised. So just to set a basis of what we're going to talk about, we can't really cover all business intelligence in 45 minutes or an hour. Every one of these systems has really three component parts at a very high level. There's some data collection mechanisms, there's some data storage, there's some data analysis. For our purposes, we're going to not talk about the data analysis simply because there's so much in the collection and storage part that I'm not going to have time to go into the excellent analysis. And a lot of the analysis was actually done using the Mathematica kernel online. So it would be a little difficult to sort of explain, I think, because it's a tool that isn't often used in this environment. So data collection, data storage in scope, data analysis next time. All right, so what kind of data are we talking about? I keep saying, oh, data, terabytes of data. What data is this? This is performance data collected by Gomez networks. Anybody familiar with Gomez? Know what Gomez is? Know what Keynote is? All very similar message systems. So for those of you who use Gomez, I'm willing to bet 90% of you are using their backbone product. This is the product that they largely use. It's very useful to help you understand the health of your system. Provides absolutely no insight whatsoever into what any user, some real poor soul with a mouse, experiences. They have another tool called Last Mile for this. The Last Mile tool lives on a local user's machine. It has an instrumented version of Firefox. It's a real browser, not some emulator, some nonsense. It's a good testing methodology. I don't want to go into a lot of it. I don't work for Gomez. I just have to deal with the data. What you're seeing here on the right is a waterfall diagram of Yahoo's front page. And boy, I don't know where my pointer is, but I think we can see right away that if I can get my laser pointer to actually work here. Probably not. You can see here we've already identified some problems even before we built the data system. More seriously, the data involved here is so large, and the difficulty of actually transmitting that data from Gomez Central back into Yahoo was so great that we basically had to go to Gomez and rebuild their system to deliver this data. So I went and designed a custom data format for Gomez. If anybody uses their FTP service, you can give me $1 or something for inventing that data format, because I went through and designed that for them and invented the FTP delivery along with Jim Pierce at Microsoft. So Microsoft and Yahoo, very large, want to do a lot of tests, get lots of data, more than 3 terabytes incoming every day. We're measuring every Yahoo page from every point in the world. Well, maybe not, but almost, right? There's 770 Yahoo properties, 770, and 112 countries. Multiply that out, do those tests every 5 minutes, it's a lot of data. So that's really what the raw data product is. And these are ASCII files. They're huge Mongo ASCII files that we gather every 5 minutes from Gomez via FTP. Now, the first question is, okay, so if there's a huge Mongo file and you grab them every 5 minutes, and what if it takes longer than 5 minutes to download that file? Well, there's your first ETL line problem. You have to remember, you got to finish your ETL pipeline in a day, or you fall behind and you'll never get out of that hole. So we actually built a parallel downloader for FTP to manage this. That's the sort of brute force, I hesitate to say nonsense because it works really well, but it's definitely a brute force engineering approach. We would not like to use FTP. It would be nice to use something a little more elegant than this old thing from the 70s. But given the volume of the data, that's where we are. And so I just want to give you an idea of what this data is. We'll talk a little bit more about it as we go forward. The data model is the star of the show here. All right, so what tools did we use for ETL? Once again, I'm doing this at Christmas. It's a prototype. I actually went and got some open source ETL program. It's called Talend Open Studio. It's very much like every other ETL tool that you use. Anybody who's used IBM DataStage or the Oracle tools will have a fair idea of how this works. And the picture here is just, this is what the IDE looks like, but we're creating the typical ETL jobs. I did not like the way that Yahoo was currently doing a lot of their ETL, which was just brute force Perl or PHP. Remember, Yahoo's a PHP shop. The guy who wrote PHP works there. They're really writing PHP to do ETL. This is not the right tool for the right job. Perl was not the right tool for the right job either. I wanted something that was going to give me just a little bit more security than writing all that stuff in Perl, a little bit more maintainability. If this system with prototype was really going to scale to the volumes that I needed it to, I was not going to get there in an error-free way with high performance doing it with Perl scripts. A lot of people do that. I decided to take a different approach. Once again, I don't work for any of these software companies. They all have their ups and downs. I'm not saying this is the greatest tool, but it worked pretty well for the project that we were working on. That's all I'm really going to say about the tool. So this is the fun part. So how do we actually get this into MySQL in some way that, remember, I'm optimizing for queries. And my users really want to see this stuff fast. And you know, it's not like, well, 24 hours delay, what happened in the performance on the website yesterday. If Yahoo has a problem with news.yahoo.com, they want to know about it before it happens. If we can't find out before it happens, we want to know as soon as we can to prevent any user from being impacted. Very short timelines. So we decided to experiment with this InfoBright engine for MySQL. It's a columnar database. I think we have all played a little bit maybe with column databases. They have their ups and downs. For this entire project, I used nothing but open source software. I did not use the commercial version of InfoBright or Talend or any of these things. I wanted not to pay any money because, remember, I had no budget. So what does the InfoBright thing give me other than, you know, it's nice to have a columnar database because that's how I'm going to make my queries, is in some column-oriented way. So I get very high compression. This is extremely valuable when I have to scale. Compression is a big deal when you have to scale, because if you have very large volumes of data and they're scattered over multiple machines, you start getting to a system where the performance of it and the errors that accumulate will start to affect your overall SLA. The InfoBright database has this thing called a knowledge grid. I'm not going to even attempt to explain to you how they claim that this thing works, because A, I don't really believe the explanation that they give me for how it works when they explain it to me. But basically what they're trying to do is perform some pre-aggregation in a predictable way on your data. And it actually works pretty well. We were able to avoid doing a lot of the standard aggregates in our database using their knowledge grid and not pre-performing all those calculations. So we'll talk a little bit about that. But once again, I don't want to concentrate so much on the tools here. I want to give you an idea of what the overall architecture and our thinking was, and then talk about what we did with the data, because that's the interesting and fun part. The tools support the project and the goals. So the other thing that the knowledge grid does is provide us a lot of query optimizations. And a lot of those are performance-based. The only thing I want to call out here is that they did give us some really serious compression. You can see, I guess you can't really read here in the MySQL GUI, but there's about 1 billion rows in this database. And it's all on the machine under my desk, 1 billion rows. That's actually pretty decent just in itself. The second stage of the prototype, we blew it up much larger and put it into the staging environment. It didn't live on the machine under my desk. But I wanted to give you an idea here. We've got a compression over the whole thing, 55x. So the other thing I haven't told you yet, I'm going to preempt my talk a little bit here and tell you, just so that you understand what 55x compression means, this is on a star schema in the third normal form. Okay, nobody quite knew what that was. All right, so we've removed the redundancy from the data, and we're still getting 55x compression. That's pretty remarkable. So how did we actually manage the data? You know, tools are great and everything, but there's a million tools. How did we manage the data? How did we actually get this stuff going? How did we manage to make it scale? My big problem here was scale, performance. I needed to do both at the same time. Not always the easiest thing. So my background is in physics. I came out of the scientific community. And one of the things that we learned in the cosmology world is how to handle very, very large data sets. Sometimes data sets that, you know, are much larger than the things that we see here. Any particular image from the Hubble telescope, for instance, is many hundreds of gigabytes. Right? This single file, it's kind of painful to deal with that. You can't imagine what the Apollo 9000s that NASA uses have. They just love those Hubble images. Regardless, my idea was I'm going to take some of the data management techniques from the scientific community and I'm going to apply it to this performance data in this commercial context. The main idea I wanted to steal was the idea of data products, organized, verifiable data sets, specific levels of abstraction. Every one of them has some very specific artifacts associated with it. The artifact list is important. There's a dictionary. We all know, I think, what these things are. There's a real data model, pre- and post-validation schemas. This particular project was big on validation. I am freaked out by the idea of database corruption. I absolutely cannot stand the idea. So there's a lot of protection in here to make sure that we don't undergo any kind of data problems. We preserve the integrity. Pre- and post-validation schemas play a role in that. There's a real life cycle plan up front. All of this was done before I wrote a line of code. I set this data model up. There's a life cycle plan. I know how long I'm going to keep every single one of my data products. I know exactly where I'm going to put them. I know exactly when I'm going to get to delete them. And I know exactly how I'm going to manage them over some long term. So given the idea of the data products, and we're going to apply this concept, let's talk about what these things really look like. The level 0 data product, it's the raw data coming in. These are zipped ASCII files, with a lot of numerical garbage in them, frankly. And a lot of this stuff is not beautiful data. It's very messy. The semantics of the data, I think anybody who's looked at performance data knows that the incoming raw data can be very noisy before you do some thinking about how to trim that data. So at the level 0, this is the raw data measurement level resolution. That's an important point. Every single measurement, every data point is preserved in the level 0 data. We also did field level syntactic and semantic validation. I'm going to explain the difference between those two things because making the distinction between the semantic and the syntactic validation allowed our ETL process to scale. And that may not be obvious how that worked just now, but in a couple slides I'll explain a little more about that. But this is an important point. The ETL process as well had to scale as well. It's not sufficient just to be able to shove a lot of data into some storage system. The entire thing has to scale. And that means that the ETL process as well. The level 1 data product is a third normal form 5-dimensional star schema. It has some concrete aggregates, but it also retains the record level resolution. I wanted to retain the record level resolution in this data because if I'm going to use this data to figure out what problems my users are having, I can't smear it out and take an hourly average. I need to be able to say, measurement made in Indonesia by this user on BPNL ISP is experiencing really slow response times or it's just unavailable. I need to be able to get at record level resolution for that. So my level 1 data products still had record level resolution. The level 2 and above data products were intended to be, when I originally wrote the data model, and this is sort of one of the traps that you can get into by planning maybe too much of everything up front, I had originally set up 4 levels of data products, and the second, third, and fourth levels were very finely done aggregates and hourly aggregates, and it was extremely fancy. Right? It turned out to be a really bad idea, and we just ended up not doing it. I decided that I did not need the aggregates. When I built the aggregation tables, it turned out it was slower than just making the queries directly and letting InfoBright handle those details for me. This is one of the things that I learned. Don't plan all that stuff too far ahead, and make sure that if you do learn something, like the aggregates are not necessary, you can drop part of what you had planned to do without a whole lot of heartache. I put a lot of effort into those aggregates, and then I had to drop them, and I was kind of hurt. So that was one of the things that I had to learn was, don't be afraid to drop things if it's not really important, and if you learn something that contradicts what you previously had considered. Data products. This is an idea that really helped save us. How did we design the ETL chains? Well, there's 70, 72. I think I was counting them this morning. I wasn't quite sure because there were a couple that I had done maybe 4 or 5 times, and I wasn't sure whether I was counting the duplicates or not. There's roughly 70 ETL jobs here. And designing all those was an art. I had spent a lot of time previously designing ETL chains with IBM Data Stage and this sort of thing, all very painful in hindsight. But it did work, and I tried to apply a lot of ideas that I had learned there to what I was doing with Talend Open Studio for this project, and it did not work. I had to relearn a lot of the things about the way that the ETL process worked, because what I found is that in this sort of distributed online, go get your data by FTP from Gomez, process it on this machine, and shove it into a machine over there, something was likely to fail. I had to build the ETL chains so that if they failed, I could run them again. Now, I've heard a couple talks here where they explain idempotency as meaning just what I wrote here. If the process fails, you can redo the job. That's not exactly what idempotent means. This is just sort of the effect of what happens when you have idempotent operations. So I want to make that distinction because that's not really the definition. That's just the effect and why you want these things to be idempotent. Really what idempotent means is that they're reversible. Intermediate steps from state to state. You want to design your ETL jobs in such a way that the boundaries around the jobs correspond to the different data states. If you're in the process of validating your data, and you haven't made the distinction between syntactic and semantic validation, and it fails, you have to perform the entire validation over again. Whereas if you carefully separate the syntactic and semantic validation and it fails, you can actually recover a lot more quickly. So identifying where the state boundaries, not really system boundaries, but a similar concept, where the state boundaries and state transitions in your ETL process are, and design your jobs to encapsulate those, is the right way to go in these loosely coupled systems. Once again, we'll treat these two things as being separate, semantic and syntactic validation. The other point that I wanted to make about designing ETL jobs, and this was something that I overlooked, and I'm hoping that you guys can learn from my mistake, is that I didn't spend a lot of time on the supporting jobs. The jobs that shard your database and roll things off the top and get rid of those FTP files once you've brought them in, and just the little supporting cleanup housekeeping stuff. I mean, it was a prototype. I was writing it over Christmas. How much housekeeping was I really supposed to do? I mean, next they were going to want me to write unit tests over Christmas. It wasn't going to happen. So I left off a lot of the housekeeping tasks, and that came back to bite me. So one thing I want to encourage you guys to do, think about what those housekeeping supporting tasks are. Data retention, how are you going to manage that? And that's data retention for each one of your data products, right? If you want to roll your FTP files off every half hour, that's one job, but it's different than partitioning the top-level volumes from your database, right? So each one of those is a small job. Don't skip them. Logging and trackback. This was another thing that I learned is in these loosely coupled systems, I really had to insert into the jobs tracking data so that if something failed, I could immediately, not after a long diagnostic process, but immediately go back and figure out what was going wrong, because my ETL chain is very tight. If I fall behind, if it fails, and I'm sitting there scratching my head for 2 days trying to figure out what went wrong, I'm toast. I'm 2 days behind. I'm never going to catch up on this ETL. So I could not really stand a long time between failures. And what that, or a long time to recover, pardon me, I said exactly the opposite of what I meant. I really couldn't stand any very long time to recover, and so I had to design these things so I could immediately go and figure out what was going wrong. After a couple times when I did not do that, boy, I learned that in a big hurry. So this is some tips on writing these ETL chains for these loosely driven systems. A lot of these things would not be done this way in IBM data stage. You would have other problems that you would have to deal with. So this is sort of specific to a lot of the open source and more modern ETL products I've seen. This is, the Talon guys are not the only ones out there. There's Kettle, there's multiple other ones. All right, so it's an eye chart. I'm sorry. It's really difficult to read, but I want to give you some idea of how this job actually accounts for the same words that I keep using with semantic and syntactic validation. Syntactic validation means that we got what we thought we were going to get. There's the right number of fields, and they're the right data types. I got 4 ints, I got 3 floats, et cetera, et cetera. I can count those things up very easily. Syntactic validation is very quick. Right? So that makes sense? The semantic validation is about what the data really means. If I have a field for a year and I do the syntactic validation on it, it's like, well, it's an int, it's got 4 digits. That's nice. But if those digits are 2525, the data does not make sense. This is the semantic validation. If I'm going to do semantic validation on that year field, I'm going to go say, oh, it's from 1900 to, what year is it? 2011, right? I'm going to talk about what the data means rather than how it's shaped. Is that sort of semi-clear? This is a really important point because the semantic validation will take much longer. And you want to be able to do it in parallel with the syntactic validation. So as soon as you have some rows that have gone through the syntactic validation, you're sure that the right fields and the right types are in the right place, you feed those immediately into your semantic validation step, which is going to take longer. You may actually run several semantic validation steps in parallel to account for the output of one syntax validation step, right? Separating these things really saved us because I was able to parallelize the ETL chains in places where it really needed it, bottlenecks in the timing here. And it actually worked out really, really well. What I actually did was I borrowed a trick from, once again, our friends at IBM and the data stage. They actually bought that, by the way. It was an acquisition. And when you find a row that does not meet the first semantic or syntactic validation check, bang, immediately goes into the reject queue. You don't look at the rest of the data. The first error automatically disqualifies that row. Hopefully, it's a syntactic error because those are easy to fix. It's almost always, there's not a quote mark around something and some text strings got concatenated or something like this, right? We see this sort of stuff all the time. It's the danger of text files. So that sort of thing, you shove it all into the reject queue, and then you have another job that goes through and says, can I reasonably make some guesses about where the quote marks ought to go in this, and reinsert them and then feed back into the rest of the chain. The semantic validation, the rejects from semantic validation are much harder to figure out. If I get a data row that says it's from the year 2525, I've got real problems. I mean, who took that measurement? And how did it get to me? Maybe this has to do with those neutrinos that are going faster than light? No. Seriously, the semantic validation and recovering from semantic validation is often much more difficult. And really, the things that go into the semantic validation queue often end up being drop data points. It's unfortunate. Not every data point can be saved. If you're going to maintain the integrity of your data set overall, it's better to drop a few data points that are iffy to preserve the integrity of the whole thing rather than be very inclusive with the data and then, whoa, you just bought yourself some corruption. No. All right, so this is the part where everybody gets to yell at me and wonder why in the world, Daniel, why did you normalize the data like that? I mean, how many talks have we heard at the conference just this week that say, we denormalized our data and boy, that really made it fast. I've heard several talks like that, and I'm sitting there going, man, my hair's going to fall out if I hear that again because I had exactly the opposite experience. So I don't want to go into too much database theory about the third normal form. You can go and get a database textbook and fall asleep reading that if you like. Basically, what it really means, what it really comes down to is we've taken all the redundancy out of the data, right? If you ran it through gzip, you would not get enormous amounts of compression because we've removed a lot of the redundancy. Actually, that's not true. We don't do character level, we do field level. But that's sort of the idea. So this data model is actually maybe the heart of the whole thing. This is what really made it work. If I had tried some denormalized data model, which I originally tried, I was following the standard orthodoxy, it did not work. Basically, that wouldn't have been very different from my level 0 data product, if you think about it. So what's up with my third normal form star schema here? Well, it's got 5 dimensions, and that's not too unexpected. I mean, we're modeling the HTTP request response cycle. You figure that model probably going to have something about the server, something about the client, something about the connection in between them. I mean, that pretty much wraps up the HTTP part of it, right? And then there's a couple additional tables for the dates. The dates are totally denormalized. I mean, totally denormalized. There's a table in there that has an entry for every day in the year. It has 365 entries. It's a very fast table to scan, right? It ends up being held in memory. So that's the level of normalization that we did. We normalized the dates and got down to the individual second, individual minute, stored all that stuff in a table. I mean, there's 86,400 seconds. That's not a great big table. Not a big deal. Oh, and did I mention one other thing? This database has no floating point fields. In order to achieve performance, you've got to drop your IEEE 754. I'm sorry. You want it to be fast? Figure out how to do everything with integers. There are no floating point data anywhere in this system. That's another act of normalization. So there's no cross-references. Remember, this is a column-based database. There's no keys. There's no indices. Well, actually, there are keys. The keys are inserted by the ETL process. But we did not use SQL's auto-increment tables. We did not try to insert the keys using the database. We actually did have references that were inserted by the ETL process, but they don't really qualify as keys in the same sense that, say, Wikipedia talks about keys. But it actually turned out to work pretty well. No integers, no cross-references. How does it actually work? Well, you have to keep track. I heard somebody, and I don't know if the young lady's here, but yesterday I heard a young lady talking about her experiences with MySQL, and she had actually run out of the end of the buffer in the auto increment in, I guess it was my ISAM, but I'm not entirely sure. And she was talking about how her database had become corrupted because the auto increment counter had circled back around and started again at 0. The little bit of advice I wanted to offer to her is that if you really want to make things extremely fast, don't have the database put those indices or those keys in there. Use your ETL process to put those in there. Let the database manage their integrity. That's pretty simple for the database to do. But you can avoid a lot of the looping around of the indices and so forth. And you can also get a little bit higher levels of data integrity if you do that process outside of the database. We'll talk a little bit about the data integrity watchdog process that I invented. It's just another Talon job that helps preserve the integrity of the system. But what I want to stress here is that we did not use the internal auto increment fields. We actually invented this for ourselves. Once again, on the normalization, I know that I am swimming upstream against the orthodoxy. Everybody says, denormalize everything. We found that it was very costly up front to get all this data into that star schema. Very highly, regulated, very solid data model for this. Very costly up front. When I went to do queries against it, it went boom. And I was able to get my users to see performance in near real time, lag times on the order of 360 seconds. That's on the last slide. I'm giving my talk away. Who plays video games? Anybody? All right, so you know when you get to the end of the level, right? And that's when the big red thing comes out, and it's really hard to kill that thing, and you've got your shotgun, you're really trying to blow it away. I usually die 10 times trying to get through the big boss battle at the end. I thought I would show you the ETL job that loads the data into that star schema. It's a boss battle of its own. If you look at the process here, and I know you can't read this. I'm really sorry. I kind of wish you could because there's something rather beautiful here in this job. But really what we do here is we go through a lot of data mongering. This is where all these validation steps take place. You can see that every single one of those has a little database canister on it. Man, this thing is really chatty. If I had one thing that I wanted to do in the next version would be to reduce the amount of chattiness that I have to do in my ETL going back and forth. The real part that I wanted you guys to see here is just, and I really wish my laser pointer was working just a little bit better, but if you look at this big block down here at the bottom, you can kind of see this is where we do the load into the star schema, and you've got these 5 database connections. Those are exactly corresponding to those 5 tables in the star schema. And you can visually sort of see how the star schema is loaded in this job. And that's sort of really interesting. Normally, we aren't able to visualize our ETL processes in some really straightforward, obvious way. And there's one cool feature of the Talon tool that I can't really show in this presentation, but you can actually run this and watch the data operations happen in real time on a very small scale. Obviously, you couldn't do that, some production environment. But just for debugging purposes, you can actually get the video game display and see, where the old Pac-Man is running through the course. It's very interesting. What I want to give you is some idea, some grasp of the level of complexity of each one of these jobs, because each of the ETL jobs here included large parts of this processing. It's common to all the jobs, loading context, managing the database, all that stuff is very common. I talked a lot about, idempotency and designing the jobs around states and so forth. I think it's really useful to be able to look at it and get the idea of kind of what's going on and sort of think about it in those video game terms rather than just have some guy standing up here sort of bloviating over some slides. Very useful to actually see what's going on. I hope you guys think that that's as useful to be able to see it as I did the first time when I was creating the job. All right, so let's talk about some of the problems that I really had to solve. The first one, and maybe the most painful one in a lot of ways, was managing URIs. So I'm building this database. It's got performance data in it. Presumably, I want to use that data to be able to track down problems, as well as manage long-term SLAs and this sort of thing. To be able to do that diagnosis, I have to have the full URL, including the get method query string, if any. That get method query string may be what caused the problem. If I chop it off in my processing and only load the base URL into the database, I'll never figure out what the devil happened when that problem occurred. So I have to store the entire URI. And anybody who's read the RFC knows that our URIs are how long? Anybody know? Baron does. What? 4,096 characters. It's defining characters rather than bytes because you got to do Unicode. 4,096 characters, man, that's a lot. So I've got some big honking text field. And of course, this is the field I want to search on, right? I mean, when I do my query, I'm going to say, give me all the measurements for news.yahoo.com the last 24 hours in Jakarta so I can go figure it out, right? So I've got to search on this big honking variable length string, and it's really painful. I think anybody who's tried to store billions of URLs in a database has gone through this problem. We came up with some clever ways of handling this. The first thing is that URIs are actually lexically scoped pretty reasonably, right? They start with a scheme identifier, and then they have a domain and a path and a query string. I mean, the spec 2965 pretty much lays out the layout of the URL. I was able to take advantage of that by using some bit fields in order to store the URLs. I mean, I know it's going to start with http:// or maybe https://, but there really aren't any other options, not for this database. So I say HTTP is 1, HTTPS is 0, and I build a set of bit strings on this. And use a set of sequential bit fields to store some of this stuff. I'm storing metadata about the URLs so that I can scope the actual searching that I have to do on the URLs down to a much smaller number than I had before. Lexically scoping these things down to a smaller set that I have to search. Some other things that I did with this. So I still can't search on this big honkin' string. I'm sorry, MySQL is wonderful, InfoBright is wonderful, but searching big honkin' billions of text strings is just not something that's an easy technical problem to solve. So what did I do? I took a SHA-1 of the URL, and I stored that with a key, and then I lexically ordered the SHA-1s, and then I could search by range. Everybody understand how the ranges work in searching? So if you know that your data is between, say, row 100 and row 200, that's another way of lexically scoping the data down to some smaller set that you have to search. But to be able to take advantage of that, you have to be able to order your strings in some reasonable way. There's no really easy way to order strings. There's all kinds of character issues and so forth. Basically created a SHA-1 hash of it, 160 bits, sorted that way. And then I go through and I search on those. There's a key that leads me off to the full URL if I need to retrieve that. A lot of times I don't need to retrieve the full URL. All I need to do is retrieve the data associated with that URL. So if you think about it, it's not entirely clear. Is the URI a fact? Is it a key? In this system, it's both, and that's sort of an interesting way of handling URLs. Actually, the SHA-1 lexical field is both a key and a data point. All right, just to be clear, the URL itself, the actual big honkin' 4096 length string, is often its own table, where hopefully I will never have to look it up. Once again, we did integer arithmetic only, and like I said, this provides significant performance improvement. Like I said, I just have a serious bug about database corruption. I just will not allow databases to become corrupt if I can do anything about it. I'm an architect by profession. I'm what I think of as a belt and suspenders architect. I want to have multiple ways to recover if things fail. I want to make sure, actually, that they don't fall, my pants don't fall down to begin with. So I invented what I call the data integrity watchdog process. And so I wanted to know if any of the data in any of the fields in the fact table ever changed. So I've got maybe 25, 30 facts in the big fact table there, and I want to know if any of them had changed since that data field was written. Well, it's easy enough to write, when the field was written into MySQL, there's a special label or data variable. It's not really a variable, but we can pretend that it is, to insert the current date into the database. That part is very simple. How do I know if things changed? Well, I took every single field in that row, concatenated them all together, and once again took a SHA hash of it. And then I stored that hash. And then I went through and looked for changes in the hash to see if any row in my table had become corrupted. The data integrity watchdog process just sits there in the background. It basically runs at a very low nice level and checks the rows of the database as often as it can to detect whether any of them have changed. This actually turned out to be very useful because I found out that there were cases where things had changed. Actually, what happened was when I was moving the data from one machine to a next, the file was truncated. I was actually trying to move, and this is sort of hokey, I was actually trying to move the MySQL data files themselves rather than extract them and then reload them. It seemed like a way to make things a little faster. I can just pick the actual database files up themselves. Some people told me they had had success with that. I did not have success with it. The data integrity watchdog saved me. I would never have realized. I mean, I got a billion rows in this thing. I can't eyeball it to tell whether it's consistent or not. By actually preserving the hash of that entire row, I could tell whether any given field had changed during the process. Most of the times, they don't change. It's a useless process. Well, not useless, but it's not going to produce any positive result. But having it there really saved me the couple times when I really did have a problem and did not realize that I had a problem. Another little best practice here, don't trade ETL time for integrity risk. If your ETL chain is going to fall behind because you don't have enough time to complete it, let it fall behind. Find some way to parallelize it, reduce jobs, do whatever you can. Don't sacrifice the integrity retaining steps in your ETL process in order to make it faster. This is exactly the wrong trade-off. Loading trash into your database really, really fastly, really, really quickly is exactly what you don't want to do, right? Don't trade off your ETL time for any risk to the integrity of the database. Are you guys getting the idea that I'm really big on data integrity? All right, more of what we learned here. Design your data products up front, but don't be really, really anal about designing those higher level data products because you don't know until you start using the level 1 and level 0 products in the real world what those higher level aggregates are really useful for. Don't plan too far ahead, but make sure that you've done some planning up front. If you start writing code with no data model, you're much more screwed than if you start writing a data model and have no code. Somebody else can write the code for you. Not having a data model is often fatal, seriously. The open source ETL works, and it scales really well. This was kind of surprising to me. I kind of thought that I was going to get to the point where the JVM was actually pretty hosed, and it wasn't able to do garbage collection anymore, and the whole thing was going to collapse, and I would be back to using C or IBM Data Stage or something. So it actually worked really well. I was very impressed. I actually went and talked to the people at Talend after that and to tell them I was impressed. And I discovered that this guy, Bill Kimball, actually works at Talend. Anybody heard of Bill Kimball? Of course you have. So Bill Kimball invented data warehousing, flat out just invented the whole dang thing himself back in mid-'70s sometimes. So he actually worked at Talend and works at Talend now, and I actually was talking to him about this. That was kind of cool. I'm like, oh, you invented it, huh? Very interesting person, and they were glad to hear that this all worked and it was scale. I don't know that anybody had really tried to do terabytes per day with their system before. This was earlier in Talend's history. Now they have a lot more customers, a lot more people are using it and enjoying using it. They have cloud-based stuff now for Hive. I haven't really played with that so much. It worked for what we were trying to do. Higher levels of normalization may well be worth pursuing. Don't let people at conferences stand up there and say, denormalize all your data, it's going to make it faster, and just believe that, swallow it whole. Test it for yourself. Maybe it's not maybe it's not the case. Maybe for your data, for your situation, for what you're trying to optimize for, if you're trying to optimize for queries, maybe the normalization path is the one that's worth pursuing. Don't just decide it's not because it's unorthodox. That was maybe the biggest takeaway that I learned here was, if you're not entirely sure, follow your own path. You can't really hurt anything by trying. Even if it had turned out that denormalization was the path to go, I would have learned something, and knowing is always better than not knowing. All right, so what was the end game? We actually got some data out of this thing. And I promised I wouldn't tell you about data analysis, so I'm not really going to. But this is the Yahoo front page. This is exactly, in fact, the waterfall that I showed you earlier. And I'm trying to tie this back to that data that I showed you earlier. This is actually a Box-and-Whisker plot. You can see I've drawn a nice little SLA line here. This is just your typical time series. And here's I'll call it a histogram rather than the probability distribution diagram. Just one thing to notice here is that the response time is actually Gaussian. But wait a minute, I thought last mile data, performance data was really noisy. Daniel, how did you get it to be Gaussian? I mean, heck, I can just look at that and see, oh yeah, the mean's 3,100, not bad. Right? How can you do that when the performance data is all over the map? Come next year and I'll explain how we do that. I don't have time to explain it this year, really. It involves some mathematical analysis about the probability distributions. What I want you to understand here is I was able to take this data, feed it into the Mathematica kernel in real time directly from the InfoBright engine in MySQL, pop these graphs out with 3,600 or 360-second lag from the time the measurement was taken. That's pretty amazing. I was really pleased with that. Now, that's a minimum. It could go up to like 8 minutes from 6. But still, pretty good. And I want to brag a little bit about that because it was a significant thing. I mean, seriously, the system that this replaced, remember this was a prototype toward building a bigger system, the system it replaced had a 24-hour lag and often didn't finish. And the reports did not go out to the executives, and they complained. So we had to put a report around the SLA, or we had to put an SLA around the reports for the SLAs. That was when I decided to write the prototype because I just couldn't do that anymore, and I couldn't have the executives coming in complaining, saying, my reports didn't run this morning. So this all worked, and it worked really well. This is the end result. End game. I actually won this video game. So that's about it. Once again, I work for PayPal. Not for Yahoo any longer. They were very gracious in allowing me to do this. Subscribe to my Twitter feed. Yes, that's a shameless plug. Other than that, I'm happy to take some questions. Everybody's sort of sitting there going, oh my God. Come on, Baron, surely you have a question. No, I don't think that you do at all, but I've just heard so many people talk about denormalizing their data to make it faster. And I found this, contentious idea where I'm swimming upstream. And I thought that was kind of one of the things I wanted to stress a little bit here is that it's an unorthodox result and it's still produced really good results. Sir? So actually what I did is I stored the next chunk of data on disk, directly on disk, manipulated it on disk, and then loaded it. It just turned out that it was a lot faster than making repeated queries. Just to follow up, I'll catch you, I promise, but just to follow up on that, what that implies is that because you're storing this stuff on disk, you don't want to overflow your disk, right? You have to have another job that monitors how your disk is doing so that you don't overrun your disk, right? So that's one of those cleanup jobs. Don't forget those puppies. Sir? So this was all done last year at Christmas. Let me repeat the question, actually. The gentleman asked me if I was doing it now rather than at the time when it was done, would I do anything different now? There's a couple things that I would do differently. I would not go the no SQL route. I know some people have asked me about that. I don't think that's an appropriate solution here. Some of the things that I might have done would be try to automate some of the data analysis tasks using MapReduce and then use a sort of an inflatable data warehouse technique where I took the output from the Hadoop jobs, the MapReduce jobs, and fed those into the relational model. And so that was one idea that I had. I haven't actually tried that because it's actually worked without it, and I didn't see the need to borrow that level of complication. But if the data source grew much larger, the data incoming, the flow grew much larger, I would probably try and go in that direction. Another thing that I would probably try to do is think about how I might distribute this globally. One of the downsides of this is no matter how fast those queries run on those machines that are serving this, if you're off-site, if you're in a Yahoo office in France or you're in a Yahoo office in Australia, it's still pretty slow, simply because it's a long way from here to there. And so if I could find some way to distribute the end products every day so that it would be a little faster in market, that would maybe be a benefit as well. Sir? So originally it was all running on a little small Linux box under my desk. That's inconsequential. When we actually blew it up into the stage one, into the staging environment, it was actually sitting on a pair of machines. I think they had 16 gigs of RAM on them because this is a RAM-heavy process. Other than that, they were pretty standard 8-core machines. So these were not miracle machines. You know, I did not whip out the Sunfires or anything to do this good stuff. Don't need any Sunfires for this, thank goodness. I don't think we make those anymore. Anybody else? Sir?
So for getting this scope from the original raw data size down to the sort of condensed data warehouse state, how much volume data you really punch through in that 500 period of time?
So the actual incoming data amounts to 3 terabytes a day. Just work out whatever that is. It's a few hundred megabytes, and it's pretty standard. Unless you change the number of tests, the amount of incoming data is pretty constant. So it's a few hundred megabytes. The end result is actually very, very small. We ended up getting an order of magnitude reduction in the data size simply through the normalization process at every step. And then once we got it into the InfoBright engine, we got additional compression around that on the order of about 55 to 1. So it's really astounding level of data reduction in terms of pure volume. And I was really pleased at that. I did not expect anything like that. I'd never used the InfoBright thing before. I basically went looking for column databases on the web, and that was the first one that looked interesting enough to actually grab. So I was really pleased about that. And the ability to get that data, I think you saw earlier, I had 1 billion rows, and it was performing really well on that machine under my desktop, which I thought was pretty remarkable. All right, I guess I'll catch my airplane early. No, not really. Does anybody else have questions? All right, how am I doing on time? Oh, perfect. All right, thank you very much.